Specifically here, I'm talking about molecules that have non-bonding electron pairs. Okay, so this could be nitrogen, oxygen, and sulfur. So this would be amines if it was nitrogen. If this was oxygen, these would be my alcohols or ethers. And then if this was sulfur, this would either be my sulfides or thiols. Okay. Again, electron impact ionization is going to remove the electron that's most accessible. The most accessible electrons is the non-bonding electron. The non-bonding electron pair on Z here to give me this radical cation. And again, recognize this is basically an alpha cleavage. Okay, where I take this electron and I'm breaking this bond that's alpha to the Z homolytically. Okay, so again, homolytic cleavage means I'm going to break this bond where this electron, one of them is going to go here to form a double bond to Z to give me this guy, and the other one's going to form basically a radical here. Why do we see this? Again, as I pointed out to you guys, we see alpha cleavage mechanisms prevalent because they always form resonance stabilized carbocations. In the case of acylium ions, I showed that. In the case of double bonds, I showed the allylic. In the case of Z, we're basically forming a resonance structure. Okay, so if this was oxygen here, right? One of the first things you learned when you learned resonance is that even though oxygen is more electronegative than carbon, the preferred resonance structure is this one because this structure has every atom with an octet. Whereas down here, this carbon's unhappy, there's only 6. So again, recognize that we're always forming resonance stabilized carbocations in the alpha cleavage. But again, the best one is this one because of the fact that every atom has an octet. Okay. So again, I'm going to show this a little bit. So ethers basically do what I just showed. I'm not going to go through it. It does an alpha cleavage. Here's the case for alcohols. Alcohols will do alpha cleavage. So here is a tertiary alcohol here. It could be primary, it could be secondary, it doesn't really matter. So again, when I do electron impact ionization, I'm going to remove the electron off the oxygen, lone pair of electrons. That's going to give me this radical cation as a molecular ion peak. Now I'm going to break this bond that's alpha to that oxygen homolytically. So again, I'm going to push this electron here, push this electron here, push that one. That gives me R dot plus this resonance stabilized system. Okay. So one of the things you should have learned with Dr. Schwann is that, aldehydes and ketones, one of the things you did in acid was you protonated them. And one of the reasons you protonate them was to make that carbon more electrophilic. Why is that carbon more electrophilic? Again, if you protonate a ketone, you get this species here. Again, this is a resonance structure in which that carbon now has a positive charge. Oops. There should not be a hydrogen here. I guess my autocorrect on my drawing apparatus put that hydrogen. So please note that there's no hydrogen there. I apologize for it. Again, alcohols and ethers can do alpha cleavage. There's another mechanism I want to share with you. Alcohols in particular can lose water. Okay, and again, as I pointed out to you guys, in the case of this system, once the molecule hits this ionization chamber and it loses water, we're losing water really as steam, as a gas. Okay, so again, this is an effective way of dissipating energy. And so, water again we're talking about losing water as gas in this instance. What one often shows is elimination in this fashion. Okay, so again, if I break this bond homolytically here and break this bond heterolytically, I form this species here, which is loss of a water molecule. Okay, so I could lose a water molecule by taking a hydrogen at the alpha position, breaking this bond homolytically to form this species here, which is basically an alkene with just a single electron. Okay, so it's positive. Okay, so that's one way of doing that. Here's another way of losing water. Okay, so here's an example of that. So this is 3-methyl-1-butanone here. Okay, so here I drew that using this. Again, 3-butanone, 3-methyl-1-butanone. The electron that has the Electron impact ionization should remove an electron from the non-bonding electron pair on oxygen, shown here. Now that I have that, if this guy and this guy comes in and this guy gets pushed and I break this bond, I form an MZ equal to 70 plus water. And so that's that peak here. Okay, loss of H2O is 18. So the important part to recognize is if you have an alcohol, first off, always look at the molecular weight of the compound, and always just subtract that 18 with the understanding that alcohols in general can lose water. Okay, so here if I lost water, this is a peak of 70 by this mechanism. Obviously, now that I have that here, once you form this molecular ion peak, it will fragment here. Why isn't this 70 peak larger? As soon as this forms, it can also undergo a secondary fragmentation. So once you start fragmenting, the molecule doesn't have to stop there. It can fragment again and again and again. So here's an example of that. Once I basically take this molecular ion peak, lose water, I form this guy. Well, this guy's just not going to stay there. It's going to actually undergo an alpha cleavage that we just talked about of alkenes. So this is just basically an alkene now with one single electron in the double bond. If I break this bond homolytically here, I'm going to make a methyl radical, and I'm going to take this electron, push it here, and push that. I form an allylic carbocation. So notice this is my MZ equal to 55, which is loss of water plus a methyl group. Okay. So again, we could continue doing this and doing this, but again, the point that I want you guys to observe here is that fragmentations will always occur to form really stabilized carbocation systems or cation systems. Here's a fragmentation pattern of ethers. Okay, so this could be another example. I could ask you this on an exam: 116, 100, 87, 57, 41, and 43. So this is how it looks. This is sec-butyl isopropyl ether. Again, electron impact ionization. I'm going to kick off that electron, get this cation here, this radical cation. Now, if I basically break, this bond here, okay, I'm going to generate this guy here plus this carbocation at 57. If I break it this way, I get this guy and that guy. Okay, how am I breaking this?
Homolytically.
No, this is being broken heterolytically. Okay, so the understanding here is you can also break certain polar bonds heterolytically. So remember on Thursday when I talked about alkyl bromides, we were breaking the bromine heterolytically because we were using the fact that bromine was a good leaving group, right? And that's something you learned in the first semester, is because halides are good leaving groups. If it leaves, you form a carbocation. Well, basically, we're breaking this bond homolytically, okay? In which I'm breaking this bond, and I'm going to break this bond towards the electron I'm breaking this bond in the direction in which the oxygen, since it's more electronegative, will receive that electron. So if you allow me this, there's a CO bond here, right? I'm going to take that CO bond and push that electron onto oxygen. So notice oxygen right here only has 3 electrons around it, right, that are non-bonding. Now it's gained 5. So if I break this bond heterolytically here, in that direction, I generate the carbocation, 57. So this is not alpha cleavage, this is not beta cleavage. It's basically cleavage of a polar covalent bond. I could also break this O carbon bond in the opposite direction, where again, I'm going in the direction towards a more electronegative element, in this case oxygen. If I push this bond this way, I generate this system here, and I generate a secondary carbocation in MZ. Okay, so notice 57 and 43 are just resulting from breaking the carbon-oxygen bond heterolytically. So the 57 and 43 are these two peaks. These two peaks here, Okay, so I haven't even done anything with alpha cleavage or of that sort. So now let's use alpha cleavage. Okay, so here's the alpha cleavage mechanisms.